Okay, so the first lecture here is on unsteady fluid flow, so transient theory. So very basics of transient. So what is a hydraulic transient? Well, it's a transition from one steady state to another. So we're talking about starting with some steady condition. You've got a water column moving in a pipe at a steady rate, and then something happens, and then eventually you reach a final steady state. So for example, there's some examples we can think of here, like ocean waves and a river that narrows. But perhaps a better example would be a valve closing. So you've got a pipe that's full of water, and you're observing the pressure over time just on the upstream side of that valve. So before it closes, and if you can see my cursor here, you have flow at a steady rate through the open valve. And then something happens, and in this case, let's say the valve closes very quickly. And you have a transient that occurs, and eventually you reach a final steady state condition. So basically the flow would be at zero, and the pressure would be at some final steady, steady pressure with the valve closed. So what happens in between these two steady state conditions is the hydraulic transient. So when we talk about a transient, that's what we're referring to. Any transition from one steady state to another, and there's many different things that can cause a transient. So some things that will cause a transient, because sometimes that change may happen very slowly, and in that case, it's still a transient. You have a transition from one state to another, but it may not necessarily generate a hydraulic surge. So, the result of a transient, a hydraulic transient, is basically a pressure wave that, carries the momentum of that whatever happens. So valve closing, pump shutting down, whatever it may be. So that energy is transmitted as a wave that propagates down your system. And if that change that occurs is relatively slow, then you may not have a significant pressure wave. So when we talk about hydraulic transients, we're usually talking about a case where there's a significant transient condition that causes detrimental change in pressure that could be a problem in your system. So basically it's a rapid change in flow. And well, what is rapid? Well, you're basically comparing that change to something called the characteristic time. So that is equal to 2 times the length of the pipeline. So from where the transient event is occurring all the way down to the end of the system. So maybe it ends at a tank or a reservoir or some final outflow point. So 2 times that divided by A, which is the wave speed. So the wave speed is the basically the velocity of that pressure wave, which can be different for different types of pipe material. So some things that can cause transients, again, valve closures, but starting, shifting, or shutting down of pumps. Also, if you have some kind of component failure or human error, like maybe a valve was closed too quickly by a hydrant operator or something like that. Also, there's some other things that can happen, such as sudden expulsion of gas, or liquid. So if a pipe bursts, for example, that can cause a transient. You have a sudden increase in flow. And there's some examples given at the bottom. The first one here is basically a pump, and you have a certain length of pipe. And what this is showing is that the downstream pipe length is greater than the upstream, and you have a certain hydraulic profile here. Your hydraulic grade may look like this, and when that pump shuts down, you have a transition to a new steady state, which might be basically the hydraulic grade being flat. But between those two steady conditions, you have a transient that may occur. Some other examples are something happening with a turbine. So maybe the electrical load is rejected, and suddenly the turbine is spinning up and you're closing a valve. Or maybe just a simple valve closure, which could be a valve to the atmosphere like a hydrant, or a valve between 2 pipes, or anything like that. All right, so why would you perform a transient analysis? Well, as I said, anytime you have a sudden change in velocity, you have a potential for a transient. And especially if you have a long, high velocity main, where if you have a transient, that's going to result in a relatively large change in velocity and momentum, which means likely a better chance that you're going to have a damaging surge. And for that reason, you want to do a transient analysis to make sure that the result of that surge or water hammer event does not cause pressures that would possibly break your pipes, burst your pipes, exceed the pressure rating. But you also may want to confirm that the low pressures are not too low. So a transient wave, a pressure wave from a transient, could be what we call an upsurge, which is basically a sudden increase in pressure, and it can also be what we call a downsurge, which is a sudden decrease in pressure. So if you hear those terms, that's what we're talking about. So we also need to check for the downsurge to make sure that we don't have pressures that are below zero that could suck in contaminants into the pipes. That could be a health hazard. Could also buckle the joints, and you can have some physical damage from that. You can also, if the pressure drops too low, you can have vapor form, which we'll talk about a little bit later, and that can subsequently cause another upsurge, a water hammer effect, which could cause even worse problems. So you definitely need to check and do a transient analysis anytime you have a sudden change in velocity or momentum. It's definitely a good idea to check for do a transient simulation and check to see if it's going to cause something that will be a problem and whether you need to do something to mitigate that. Now, distribution systems tend to be, too complicated for, simple methods that you might do by hand or on paper or, rules of thumb equations. You really need a computer model to, properly analyze everything that happens during a complex transient event to really get a good assessment of what is going to happen and is it going to be a problem, because oftentimes you'll find some interesting phenomenons or things that you wouldn't think would happen, but once you do a transient simulation using Bentley Hammer, you'll realize, oh, this may be a problem here. And then the final point here is that the cost of doing an analysis can be far less than the cost of even a single repair. So basically the cost of Hammer and being trained with Hammer and spending your time doing the transient analysis is well worth your time. Okay, so some fundamentals. Pressure waves as a result of a transient, they travel very fast and they can reflect at dead ends and interact differently at different types of elements. The total pressure is the sum of each pulse's energy at that location and time step. So basically things are very complex when you have these pressure waves traveling. They may interact with other pressure waves that are tying in from other pipes, and you can have some very complex interactions. So you really need a computer model like Hammer to properly analyze those things. Subatmospheric pressures, as I said before, they can be very critical. And that makes the difference when you're setting up a profile and deciding, which junctions to include, which elevations to include in your model. If you have a simplified profile of, say, just a single pipe, you may be missing out on intermediate high points that could potentially cause subatmospheric pressure, which, as I said, you need to check to make sure that, your pressure is not too low or that a vapor pocket does not occur. So you really need to, be careful about setting up, what elevations you include and making sure that those elevations are accurate. And those elevations should be the pipeline elevation, because that's the point that we're measuring the pressure from. And it's significant when we're talking about, at what point does vapor form. So we need to be, consistent with that. Okay, so you may have seen this before, but this is a sort of rule of thumb for calculating what your change in head would be as a result of something that we would, in quotes, be a rapid closure. So again, when we say rapid or fast, we're talking about occurring quicker than your characteristic time, the 2L divided by A. So if you have for example, a valve closure that's happening that quickly, you could follow this Joukowsky equation here in green to estimate what the change in head, your water hammer pressure surge would be expressed in length units a head, by taking the wave speed of the pipe and dividing it by gravity and then multiplying it by the change in velocity. So for a simple valve closure, you've got some initial velocity through the valve, and that's dropping to 0. So your delta V there is the initial velocity. So you can pretty quickly calculate what the pressure surge would be, and this is just a rule of thumb again. So you can see, okay, well, is that going to be exceeding my pressure rating of my pipe or not? And maybe if it's nowhere near close, then maybe you decide you don't need a transient simulation. But if it is, then instead of just saying, well, that's, we have to do something and provide some protection, what you really want to do is then go ahead and actually do a full transient simulation in Hammer, because as I said, there can be other complications and other interesting things that contribute and could, even make things worse than that simple rule of thumb there. But just following the equation, you can see basically if you stop 1 meter per second, valve with a flow of flow velocity of 1 meter per second, if you're stopping that instantly down to 0, then that's following this equation, that's an upsurge of basically about 100 meters. So you can see just from that how significant we're talking here. So what we're going to do is switch back to Hammer, and I'm going to show you just a quick demo. But what I'm going to do is show you quickly the results of a simple transient analysis and kind of validate the Joukowsky equation and also show some concepts about wave propagation. So I'm going to go ahead and bring up Hammer here. What we have here is a sample that's included with Hammer. It's sample 1. This is just a very simple one-pipe model. You have a reservoir at about 300 meters, and that's leading to a valve, which we're going to close instantly at the very first transient time step. So it's the other important point here is this is a frictionless system. So this is simplified to show you what happens without the effect of friction. What happens to those transient waves that are propagating in your system. So I've already computed this model, so I'm just going to go ahead and show you the transient results right away. Again, don't worry about the details yet. I will show you, and you will see in further slides and also later in the workshop how to actually open these things and do these things. But what we're seeing right here is a profile view of that pipe. You can see the distance. It's a 1,000-meter long pipe. And the black line here is our starting steady state. Again, a transient is a transition from one steady state to another. In this case, since we have a frictionless system, the black line here, which is our initial hydraulic grade, is basically flat. So the reservoir is on the left and the valve's on the right. So what we're going to do here is simulate what happens when this valve on the right closes instantly. So if I advance the slider here, we can see in the very first transient time step we have an upsurge in pressure. So a spike, a rapid increase in pressure, and it's quite significant here. It's gone from about 300 to about about 150 meters of head change there. And if we were to look at the velocity through this pipe and the fact that we're instantly changing that to 0, if we were to put that through the Joukowsky equation, we would get just about the same that Hammer is giving us here. It's about 150, I think, meters of head based on the wave speed of this pipe. So what's going to happen here, as I advance to the next time step, you'll see that this pressure wave is moving to the left, and the rate at which it moves is the wave speed of your pipe, which you enter in the pipe properties. So what's going to happen is that's going to propagate down the system. If I advance forward a little bit, you will see eventually we'll get to the point right here when that pressure wave has reached all the way down to the upstream end of the system at the source reservoir. And at that point, basically, the entire water column in this pipe has its molecules packed together, so to speak, and the pressure has increased throughout that entire profile. So basically, as you're moving along in time, more and more molecules are packing up against the next molecule, almost like a car collision on a highway. More and more cars will pack up behind it. So eventually, that pressure wave reaches the end, and this is an open reservoir, so if I advance to the next time step, it reflects off of that endpoint, and you can see that is then traveling back towards the valve. So you can see it has decreased. It has, first we increased the pressure, and that wave has moved all the way to the upstream end of the system, and it's reflected as basically back down to the initial pressure. And that's going to then propagate down to the end and all the way down to the valve. And we're at only 2 seconds into the simulation. So you can see with the wave speeds that you typically have in Hammer or for a transient simulation, these are happening at very, very small time scales. So when that pressure wave has then reflected back to the valve as I won't call it a low pressure, but it's reflected back with the same amount. So we're back down to the initial pressure, but once that hits the valve, it then reflects off the dead end, because the valve is a dead end, whereas the reservoir is an open reservoir. In this case, it's reflected back as a negative pressure wave. And if we continue moving forward, that's going to reflect back and travel back to the reservoir. And just like we saw before, when that reaches the reservoir and bounces back, it's then reduced back to the initial pressure. And that's going to bounce back and forth forever in this case, because we do not have friction. So this is a very important point. Without the presence of friction in your pipe, there is nothing to dampen the surge wave, and it will bounce back and forth forever. So it's the friction in your pipe, the resistance from friction, that will reduce and dampen these pressure waves over time. So, and this can be very significant, because in some systems like this, where you have a valve closed, you basically have zero flow in this pipe during this process. Not quite zero. You have a small amount of movement of water at the endpoints because of the line packing that occurs from the molecules packing up against each other. But from that little bit of movement, with some friction incorporated, you can actually see this transient wave dissipate over time. But if I just kind of fast forward here, we can see it bounces back and forth, back and forth. It never decreases. And in some real systems, once you're actually using Hammer, if you have a certain segment of piping that is completely closed off during a transient, such as between a pump and the upstream reservoir, you can have this situation. If your pipe has very little friction, or there's a problem with the setup of the pipe and the friction factor is not being used properly, you can have a wave bounce back and forth, and you can see transient phenomenon that basically never stops. And that's because you need that component of friction to dissipate the surge. And even in a real system where friction factors are all okay, if you have things being closed off and eventually your flow reaches zero, if you still have pressure waves traveling back and forth from the surge event, then you can have this type of situation where it appears that the pressure wave never really fully dissipates. And that's a main factor of that is the flow in the pipe. So what we're going to do here is also show you a time history. So a time history is basically a graph. So if I look at a graph of, let's say, pressure and flow next to the valve that's being closed, we can see here it starts at 1,000 liters per second, goes to 0, and then we see the result of the pressure waves reflecting back and forth. We see that it never really dissipates. So as we move through time, we're seeing an upsurge occur here, and as it reflects back, we eventually see the downsurge, and it keeps reflecting back. This never dissipates. If you had significant friction factors, you would see these lines eventually reach a final steady state, which is normally what you would have in a system. You're going from one steady state condition to another, but sometimes that does not happen. So the main purpose of this little demo here is just to kind of quickly show you a very simplified Hammer model and the impact of wave propagation and reflection, and the impact of friction. And this is a very simplified approach, and we'll get into much more complicated situations. So back to the slides. So again, key points for that little demo. Wave propagation continues forever without friction. The way that the wave reflects is different depending on what it reaches. So a reservoir is an open, water source, whereas the closed valve is a dead end, basically. So the way the wave reflects acts differently depending on those types of boundary conditions. We don't see, low pressures that are too significant to be concerned with, but it's possible if there's other piping downstream of the valve, that might be a concern there, because there might have been a downsurge wave that traveled further downstream that could have an impact on the rest of the system that we may need to look at. And also, there was no vapor or air that formed in the system. We did not introduce any air valves, and we didn't have any vapor pockets forming.
If you found this video helpful, please give it a like. If you want to see more such series, consider subscribing to our channel. Thank you, and see you next time.